This problem is similar to the one we just did, except that we're on a 30-degree ramp. So for the sake of this problem, let's assume that some kid's got a little toy cart, and let's say the cart is 10 kilograms, so the mass of this object here is 10 kilograms. And it starts at rest, so he puts it up here at the top of a ramp, and it's starting at rest, and he lets it go, and it goes down the ramp till it reaches the bottom over here, where it finishes right over here. And right over here, if you could measure it, we're going to say that the final velocity is 3 meters per second. And what we want to do is find or calculate the length of the ramp, the distance that the cart or the car, little toy cart, travels from the top to the bottom. You want to know the distance. And we want to use the work energy theorem to find or calculate that distance. So our work energy theorem tells us that the work done by the net forces, or the net work, is the change in the kinetic energy of the object. Now our kinetic energy is always 1/2 mass times the velocity of the object squared. So if we want to know what our change of kinetic energy is, that's the final kinetic energy minus the initial kinetic energy. In this case, what's the initial kinetic energy? 1/2 mvi squared, but vi is 0. Since it's at rest, it has no kinetic energy, so the initial kinetic energy is 0 joules. What about the kinetic energy here, the final kinetic energy? Well, the final kinetic energy is simply going to be 1/2 the mass, which we said is going to be 10 kilograms, times the velocity squared. So our final kinetic energy is going to be 45 joules. All right, so we can calculate that quite easily because we're just dealing with velocities. First case, it's 0, so that's 0 kinetic energy. At the finish, the final kinetic energy is 1/2 mv squared, where we said that the final velocity was 3. So that comes out to 45 joules. So our change in kinetic energy, our delta K, is K final minus K initial. That's the change, the final minus the initial. And that's simply going to be 45 minus 0, which comes out to 45 joules. So we know the final kinetic energy, we know the initial kinetic energy, we know the change in the kinetic energy. So that tells us the answer to the net work that is done by all of the forces, or the work that's done by the net force in moving the object down the ramp. So that tells us we need to find the forces. So that tells us force diagram or free body diagram. Now whenever you have a ramp, I always suggest that we draw in a axis, I'm going to pull my axis here, that is going to be perpendicular to our ramp, and let's at the same time draw one parallel to the ramp. So there's our axis. It's kind of like a twisted or rotated XY axis. And now we're good to draw in our forces. So let's draw in our weight. Weight of the object is going to go straight down. So there's my weight. And I'm going to draw on the weight here. That's weight, W. Then we have the normal force, N. And I'm going to put the normal force in, let's use this color for the normal force here. That's going to be N. And then we have a force of friction, don't we? And friction always goes up the ramp if things are moving down, because it's always going the opposite direction. So let's put friction in red, since it tends to be the bad guy all the time, causing resistance to the movement. So there is our force of friction. And since this is moving, I'm going to put an F sub K for kinetic friction. So there I got 3 forces, the yellow weight, the green normal, and then the red force of friction. And that's it. Those are the 3 forces that are always going to be acting on any object in a plane. Now we're almost done. All we have to do is take that yellow weight vector and resolve it into 2 components put those two components on the green axes that we just drew over here, the perpendicular guys. Now I told you before, and I'm going to do this in yellow so we keep everything, that if this guy is 30 degrees, then what you have right in here, all right, is 30 degrees. So this is 30. It's very hard to do it, but I'm going to put 30 degrees right in there. That's the angle 30 degrees. So we have a component of the weight heading this way, and that's always going to be the weight. By the way, what is weight? Weight is simply mg, isn't it? It's mg. So this component is going to be the mg sine of 30. And then this component along that direction is going to be mg cosine of 30. And I hope you can still see that. So we took this yellow weight vector that's going straight down, we made it mg sine 30 along the path parallel to the plane, and then in the normal direction mg cosine 30. And now we're done. We don't have to worry about anything else here. We know that the normal force then is going to be balanced with the mg cosine 30. So our normal force in this case has to be balanced with this guy over here. So our normal force then will have to equal the mg cos 30 force, because you have to have the green up has to equal the yellow down along that axis. Because we're in equilibrium and we're not moving up or down in this direction, so the forces up have to equal forces down along the same line. So what would that be? mg, if this is 10 kilograms, 10 times 9.8 is 98. 98 times the cosine of 30 is what? I have roughly 85. So let's call it 85. 85 newtons. So 85 up, 85 down. Now, mg sine 30, mg again is the weight, mass 10 times 9.8 is 98. 98 times the sine of 30 is 49. So that's 49 newtons. Now what about the force of friction? We stood to do that in red, so let's put it here. The force of kinetic friction, remember the formula, is this guy mu k times the normal force. And I'm going to tell you for this problem, let's just assume mu k is 0.2. It could be something different, but just to pull out a number, let's just say 0.2. So mu k is going to be 0.2. The normal force is n, that we just calculated. N has to equal this component here, mg cosine 30. So that's 85. And so the force of kinetic friction then is 17. If I'm doing the math right, 17 newtons. So we got 17 newtons over here up the ramp. So good. So far, so good. So what's our net force? Remember, net force, and you might say, Mr. Beatty, why am I trying to find the net force? Well, the net work is equal to the net force times the displacement, d. Because remember, work, I always remember work as force times distance. That's how I remember work. And I always try and find all the forces that are lined up parallel to the displacement. Okay, so if I have something that's off at an angle, I'll resolve it into components, because you know that when you're calculating work, if you have, let's say you have some vector like this is the force, right? And the displacement is actually this way, and you've got some angle over here. You want to take that force vector and resolve it into component this way and a component that way. This component is going to be F cos theta. And this component here does no work because it's perpendicular to the displacement. So you'd have this times the d. So I'm already, if this vector and the displacement vector are in the same direction, then theta is 0, cosine theta is 1, so it's just force times distance. Anyway, we need to find the net force to find the net work. This net force, we know up and down on this axis, these cancel out, leaving us simply the friction and the 49 newtons. So it's going to be 49 minus the friction, which we said was 17. And if we do that, the net force is going to be 32 newtons. So then, the work done by the net force is going to be work net is change in kinetic energy, which we said before was 45 joules. Here it is here. We figured it out there. And this is going to be force net times distance has to equal that 45. The net force we said was 32. 32, that's our net force. Put that here. Times the distance is 45. So our distance then is going to be 45 divided by 32, which is 1.41 meters. And that's how we use the work energy theorem to calculate the distance. And I hope that helped, and I hope that I'm within time frame for posting this. See you next time.